Imagine gazing at the night sky, assuming everything obeys the laws of physics as we know them until scientists discover quasars billions of light years apart, mysteriously aligning in perfect patterns. This isn't science fiction. It's a real cosmic puzzle defying our understanding of space itself. What if I told you this is just one of 30 invisible forces secretly shaping reality? Forces so strange they rewrite the rules of existence. From ghostly particles that phase through planets to dark energy ripping the universe apart, these phenomena remain hidden in plain sight. Today, we're pulling back the curtain on the unseen machinery of the cosmos forces that govern everything from the tiniest atoms to the largest galaxies. Buckle up, because by the end of this journey, you'll question whether reality is as solid as it seems. Let's dive into the first force, the quantum chaos lurking in what we call empty space. Now let's peel back another layer of cosmic mystery. What if I told you that nothing doesn't actually exist? Even in the darkest, emptiest corners of space, there's a hidden frenzy of activity. This is the realm of quantum vacuum fluctuations, where so-called empty space is anything but empty. Picture a bubbling cosmic soup where particles and their anti-particle twins constantly blink in and out of existence, dancing on the edge of reality. These aren't just theoretical oddities, they're the invisible architects shaping everything from the glue holding atoms together to the very fabric of space-time itself. One of the most mind-bending confirmations of this quantum chaos comes from the Casimir effect. Imagine two metal plates placed incredibly close together in a vacuum, so close that the buzzing virtual particles outside them overpower the limited activity between them. The result, the plates get pushed together by the sheer pressure of nothingness. Dutch physicist Hendrik Casimir predicted this in the 1940s, and decades later, experiments proved him right. It's as if the universe itself is whispering that emptiness is an illusion. But the influence of these quantum fluctuations runs even deeper. They're the reason atoms don't instantly collapse. Electrons orbiting a nucleus should, according to classical physics, spiral inward and vanish in a fraction of a second. But thanks to the relentless jitter of virtual particles, they stay stable, refusing to let matter crumble into oblivion. Even the expansion of the universe might owe a debt to these fleeting particles. Some theories suggest dark energy itself could be fueled by vacuum fluctuations stretching space-time apart. What's truly humbling is realizing that this quantum turmoil isn't some distant cosmic phenomenon. It's happening right here, right now, beneath your fingertips. Every cubic centimeter of so-called empty space is a seething ocean of potential, where particles flicker into being and vanish faster than the blink of an eye. So the next time you gaze at the night sky and see vast stretches of darkness, remember, there's no such thing as true emptiness. The universe is alive with hidden forces, and we're just beginning to decode their secrets. Now, let's venture deeper into the cosmic unknown, where the fabric of the universe is woven by something we can't even see. Imagine a spider's silk, invisible but unbreakable, holding galaxies together in a vast cosmic web. This is the enigmatic realm of dark matter, a ghostly substance that makes up roughly 27% of the universe yet leaves no trace of light or energy. It's the universe's best-kept secret, detectable only by the way it tugs on everything around it with its gravitational pull. For decades, scientists were baffled by the way galaxies move. According to Newton's laws, stars at the edges of a galaxy should orbit slower than those near the center, just like planets farther from the sun move more sluggishly. But when astronomers like Vera Rubin studied galaxy rotation curves in the 1970s, they found something startling. Stars at the outer edges were whipping around just as fast as those near the core. The only explanation, some invisible mass was holding the galaxy together, a gravitational glue we now call dark matter. Without it, galaxies would fly apart, their stars scattered into the void. But the evidence doesn't stop there. One of the most dramatic confirmations of dark matter's existence comes from the Bullet Cluster, a cosmic collision over 3.7 billion light-years away. When two galaxy clusters smashed into each other, their hot gas, the visible matter, slammed together and slowed down, while dark matter, unaffected by electromagnetic forces, kept racing ahead. By mapping the gravitational lensing how the cluster warps the light of distant galaxies, scientists could actually trace the dark matter's path, revealing it as a separate, invisible entity. It was like watching a ghost walk through a wall, leaving no footprint but bending reality itself. What's even more mind-bending is that dark matter isn't just lurking in distant galaxies, it's all around us, streaming through your body right now. Millions of these particles might pass through you every second, yet they interact so weakly with ordinary matter that you'd never notice. Some theories suggest dark matter could be made of WIMP, weakly interacting massive particles, or even primordial black holes born in the universe's earliest moments. But despite decades of searching, we still haven't caught one directly. Dark matter isn't just a cosmic curiosity. It's the unseen architect of the universe, the hidden scaffolding that shapes everything from the tiniest dwarf galaxies to the largest superclusters. And as we peel back its mysteries, we're not just learning about the darkness, we're rewriting the story of reality itself. Now, let's shift our gaze from the invisible threads holding galaxies together to an even more puzzling force, one that's not just hidden but actively working against the fabric of the cosmos. Imagine the universe as a balloon being inflated, not by someone's breath, but by something far stranger. This is the realm of dark energy, a mysterious pressure that makes up roughly 68% of the universe and is causing it to expand faster and faster, defying gravity's relentless pull. For centuries, scientists assumed the universe's expansion was slowing down, just as a ball thrown upward gradually loses speed to gravity. But in the late 1990s, two teams of astronomers made a discovery so shocking it earned them the Nobel Prize. By studying distant supernovas, exploding stars that serve as cosmic yardsticks, they found the opposite. The universe's expansion wasn't slowing. It was accelerating, as if some invisible hand had given the balloon an extra, unexpected kick. The culprit, dark energy, a repulsive force woven into the very fabric of space itself. What makes dark energy so baffling is how it flips our understanding of gravity upside down. While dark matter's gravity pulls galaxies together, dark energy pushes them apart, and its influence grows as the universe expands. Think of it like this: if you pour more coffee into a mug, the liquid doesn't dilute. Instead, it becomes stronger. That's dark energy. The more space stretches, the more dark energy there is to stretch it further, creating a runaway effect that could one day tear galaxies, stars, even atoms apart in a theoretical Big Rip. But where does this strange energy come from? One leading theory points to the cosmological constant, an idea Einstein once proposed and later dismissed to explain empty space's inherent energy. Another suggests it might be a dynamic field, like an invisible fluid filling the cosmos. Yet despite decades of research, dark energy remains as elusive as ever. We see its effects in the way galaxies flee from each other, in the faint echoes of the Big Bang's afterglow, but we still don't know what it truly is. Here's what's truly humbling: dark energy wasn't always in charge. For the universe's first 9 billion years, gravity dominated, slowing the expansion. But around 5 billion years ago, dark energy took over, and now it's calling the shots. Some scientists believe this shift might be a clue to dark energy's nature, hinting that its strength isn't constant but changes over time. Others worry it could mean our understanding of gravity itself is incomplete, forcing us to rewrite the laws of physics. Dark energy isn't just a cosmic mystery, it's a countdown clock for the universe's fate. Will expansion continue forever, leaving galaxies isolated in an ever-cooling void? Or will dark energy's push grow so strong it shreds reality itself? For now, the answers remain hidden in the darkness, waiting to be uncovered by the next generation of telescopes and cosmic detectives. One thing's certain: as we peer deeper into this enigma, we're not just studying the universe's expansion, we're reading its final chapter. Now, let's rewind the cosmic clock, way back to the universe's first fleeting moments, when reality underwent a growth spurt so extreme it makes dark energy's push seem sluggish. Picture this: in less than a trillionth of a second, the universe ballooned from smaller than an atom to the size of a grapefruit. This wasn't just expansion, it was cosmic inflation, a turbocharged stretching of space itself that set the stage for everything we see today. What's wild about inflation isn't just its speed, but how it solves two of cosmology's biggest puzzles. First, the horizon problem. Look at the cosmic microwave background, the afterglow of the Big Bang, and you'll see the same temperature everywhere, like a perfectly baked cookie. But without inflation, these regions couldn't have exchanged heat, leaving scientists baffled. Inflation fixes this by suggesting everything we see was once crammed into a tiny, ultra-connected dot that got stretched smooth. Then there's the flatness problem. The universe's geometry is eerily balanced, not too curved, not too warped, like a pencil standing perfectly upright. The odds of this happening by chance are astronomically low, but inflation explains it. Imagine stretching a crinkled bedsheet until it looks flat. That's what happened to space-time, smoothing out any kinks in the universe's shape. But how do we know inflation wasn't just a clever idea? The smoking gun lies in gravitational waves, ripples in space-time predicted to arise from inflation's violent stretching. While we haven't detected these primordial waves directly, their fingerprints are all over the cosmic microwave background. In 2014, scientists working with the BICEP 2 telescope thought they'd spotted these imprints, though dust clouds muddied the results. The hunt continues with next-gen observatories like the Lightbird satellite, poised to listen for inflation's echoes. Here's where it gets even stranger. Inflation suggests our universe might be one bubble in a frothing multiverse, where other bubbles undergo their own inflationary bursts, and the energy driving inflation. It's tied to a hypothetical field called the inflaton, which, much like dark energy, permeated space before vanishing, leaving behind the universe we know. Some theories even propose that dark energy is a faint shadow of this primordial force, a cosmic déjà vu billions of years in the making. What's breathtaking is how inflation links the quantum to the cosmic. Tiny quantum fluctuations during this rapid stretch got magnified into the seeds of galaxies. Without those microscopic ripples, stars, planets, even us might not exist. It's a humbling thought. The largest structures in the universe owe their existence to subatomic tremors in the first unimaginable fraction of a second. As we piece together inflation's legacy, we're not just uncovering the universe's birth, we're decoding the instruction manual for reality itself. And with every new telescope probing the cosmic microwave background, we edge closer to answering the ultimate question: what really happened when everything began? Now, let's take a leap into one of the most mind-bending ideas in modern physics, the holographic principle. Imagine if everything you see, touch, and experience in our three-dimensional world was nothing more than a projection, like a movie playing on a cosmic screen. That's the essence of this radical theory. Our reality might be a hologram encoded on a two-dimensional surface at the edge of the universe. This idea didn't come out of thin air. It emerged from the study of black holes, those cosmic vacuum cleaners where gravity is so intense that not even light can escape. In the 1970s, physicist Jacob Bekenstein made a startling discovery: black holes have entropy, a measure of disorder, and it's tied to their surface area, not their volume. This was bizarre because entropy usually depends on how much stuff is inside a system, not its outer shell. Then came Stephen Hawking, who showed black holes aren't entirely black. They slowly leak radiation and can evaporate over time, but here's the puzzle. if a black hole vanishes, what happens to all the information it swallowed? Quantum mechanics says information can't be destroyed, but general relativity suggests it's lost forever. This contradiction, known as the black hole information paradox, led physicists to a wild solution. Maybe the information isn't inside the black hole at all. Maybe it's plastered on its surface like a cosmic sticky note. This is where the holographic principle kicks in. The theory proposes that all the information needed to describe our three-dimensional universe could be encoded on a two-dimensional boundary surrounding it, like how a hologram stores a 3D image on a 2D film. In other words, the rich tapestry of stars, galaxies, and even you and me might just be data painted on the universe's outer edge. The implications are staggering. If true, it means the universe operates like a giant quantum computer, with space-time itself as a projection of quantum bits. Some versions of string theory even suggest that gravity, the force shaping the cosmos, emerges from this lower dimensional code. Think of it like a video game. The stunning graphics you see are just the output of underlying code running on a flat screen. But how do we test something this abstract? Scientists are looking for clues in the cosmic microwave background, searching for anomalies that might reveal the universe's pixelated nature. Others are simulating holographic models in labs, using ultra-cold atoms to mimic how information might behave at the universe's edges. Even more intriguing is how this principle bridges two seemingly incompatible theories: quantum mechanics and general relativity. By treating spacetime as a hologram, physicists might finally crack the code of quantum gravity, the holy grail of modern physics. So the next time you look up at the night sky, consider this. The vast three-dimensional cosmos might just be the universe's grandest illusion, a shadow cast by something far simpler yet infinitely more profound. And as we peel back the layers of this cosmic mystery, we're not just redefining reality, we're rewriting the rules of existence itself. Now, let's shift our focus to one of the most elusive and baffling phenomena in particle physics: neutrino oscillations. Picture this: tiny, nearly massless particles born in the hearts of stars or powerful cosmic events, zipping through space at nearly the speed of light. But here's the twist: these particles don't stay the same. They morph from one type to another as they travel, like cosmic chameleons defying the laws of classical physics. Neutrinos are often called ghost particles because they barely interact with matter. Trillions pass through your body every second, leaving no trace. For decades, scientists thought they were massless, just like photons. But in the late 1990s, something extraordinary happened. Researchers observing neutrinos produced by the Sun noticed a discrepancy. The number of electron neutrinos arriving at Earth was far fewer than predicted. This became known as the solar neutrino problem, and it puzzled physicists for years. The breakthrough came when we realized neutrinos weren't disappearing, they were changing. These particles come in three flavors: electron, muon, and tau neutrinos. As they travel, they oscillate between these types, a phenomenon only possible if neutrinos have mass, however slight. This discovery shattered the standard model of particle physics, which had assumed neutrinos were massless. Suddenly, we had to rewrite the rules. But how does this work? Think of neutrinos as a trio of intertwined waves. Each flavor is a mix of different mass states, and as the waves propagate through space, their interference causes the neutrino's identity to shift. It's like a musical chord where the notes change as the sound travels, revealing new harmonies along the way. The implications are profound. First, neutrino oscillations prove that there's physics beyond the standard model, hinting at undiscovered particles or forces. Second, they offer clues about the universe's matter-antimatter asymmetry, why we live in a cosmos dominated by matter rather than antimatter. Neutrinos might hold the key to this cosmic imbalance. Today, experiments like Super Kamiok and in Japan an ice cube in Antarctica are unraveling these mysteries. By detecting neutrinos from the Sun, supernova, and even particle accelerators, we're piecing together how these shape-shifting particles influence the universe. From stellar explosions to the quantum fabric of reality, neutrinos are silent players in the grand cosmic drama, proof that even the smallest things can rewrite the rules of existence. Now, let's venture into another cosmic puzzle, one that challenges our very understanding of magnetism. Imagine a magnet. You know it has a north and a south pole, right? Break it in half, and you'd expect to get two smaller magnets, each with its own pair of poles. But what if I told you there's a hypothetical particle that defies this rule, a solitary north or south pole floating freely in the universe? This is the elusive magnetic monopole, a particle that has never been observed but whose existence could rewrite physics as we know it. The idea of magnetic monopoles isn't new. Back in the 19th century, James Clerk Maxwell's equations, the foundation of classical electromagnetism, hinted at their possibility, yet for over a century no one could find one. Then came grand unified theories, or GUT, which attempt to merge the electromagnetic, weak and strong nuclear forces into a single framework. These theories predict that in the extreme energies of the early universe, monopoles should have been produced in abundance. So where are they? This glaring absence is known as the monopole problem, and it's one of the strongest clues we have for cosmic inflation, the rapid expansion of the universe moments after the Big Bang. Here's why monopoles matter. In grand unified theories, these particles are like cosmic relics, remnants of a time when the fundamental forces were indistinguishable. They'd be incredibly massive, possibly as heavy as a bacterium packed into a single particle, and carry a magnetic charge so strong it could disrupt atoms. If they were as common as GOTs predict, the universe should be swarming with them. But despite decades of searching in lunar rocks, ancient meteorites, and even with particle colliders, we've found zero evidence. This mismatch between theory and observation led physicists to a radical solution: cosmic inflation. The idea is that the universe expanded exponentially in a fraction of a second, stretching space so rapidly that any primordial monopoles were diluted to near non-existence. Inflation doesn't just solve the monopole problem, it also explains why the universe appears so uniform on large scales and why it's geometrically flat. In a way, the absence of monopoles is silent evidence for one of the most dramatic events in cosmic history. But the hunt isn't over. Some theories suggest monopoles might still exist, hidden in the far reaches of space or trapped in exotic materials. Experiments like MOEDL at the Large Hadron Collider are actively searching for them, while astrophysicists scan the skies for their telltale signatures. Finding even one would be a Nobel Prize-worthy discovery, confirming a piece of physics that's been theoretical for over a century. Whether they're out there or not, magnetic monopoles remind us that the universe is full of unanswered questions. Their theoretical existence pushes the boundaries of our knowledge, and their absence shapes our understanding of the cosmos's earliest moments. From grand unified theories to the inflationary Big Bang, these phantom particles are a testament to how much we still have to learn and how the missing pieces of the puzzle can sometimes reveal the most. Now, let's unravel one of the most baffling phenomena in quantum physics, a force so strange that even Einstein called it spooky action at a distance. Picture two particles, maybe electrons or photons, born from the same event. They become entangled, their fates forever linked no matter how far apart they drift. Measure one, and its partner instantly reflects that measurement, defying the speed of light and our classical intuition about how the universe should work. This isn't science fiction. Quantum entanglement has been tested repeatedly, with experiments growing more sophisticated over decades. At the heart of it is Bell's theorem, a mathematical framework developed by physicist John Stuart Bell in the 1960s. His work proved that if quantum mechanics is correct, entangled particles must influence each other in ways that can't be explained by hidden variables, secret properties determining their behavior in advance. The implications are staggering. Either particles communicate faster than light, which relativity forbids, or the universe isn't as locally real as we thought. For years, skeptics proposed loopholes, gaps in early experiments that might explain the results without invoking spooky action. Maybe the detectors weren't efficient enough, or the particles somehow knew the measurement settings in advance. But in 2015, a landmark experiment closed these loopholes decisively. Scientists led by Ronald Hansen at Delft University used entangled electrons in diamonds separated by over 1 kilometer. Their measurements were so precise and random that any hidden variable theory would require signals traveling faster than 10,000 times the speed of light to explain the correlation. The universe, it seems, prefers spookiness. Why does this matter? Entanglement isn't just a curiosity. It's the backbone of emerging technologies like quantum computing and cryptography. A quantum computer leverages entangled qubits to perform calculations exponentially faster than classical bits, potentially revolutionizing fields from medicine to materials science. Meanwhile, quantum encryption uses entanglement to create unhackable communication channels where any eavesdropping disrupts the delicate link between particles. But the deeper mystery remains. How does nature pull off this trick? Some theories suggest entanglement hints at a more fundamental layer of reality, where space and time emerge from a web of quantum connections. Others propose it's evidence of a holographic universe, where what we perceive as separation is just an illusion. Whatever the answer, entanglement forces us to rethink the very fabric of existence. One thing's certain: the universe is far weirder than we imagined, and entanglement is proof that the cosmos still holds secrets waiting to be uncovered. Now, let's shift our gaze to a cosmic mystery closer to home. Well, closer in galactic terms at least. Hidden behind the thick veil of stars and dust in the Milky Way lies something massive, something pulling our entire local group of galaxies toward it with a gravitational grip we can't ignore. This is the Great Attractor, a gravitational anomaly so powerful that it defies our expectations of how matter should be distributed in the universe. Imagine the Milky Way, Andromeda, and dozens of smaller galaxies all drifting through space, not at random, but toward a single point. Astronomers first noticed this strange motion in the 1970s when mapping the cosmic microwave background, the afterglow of the Big Bang. They expected to see galaxies moving uniformly outward, but instead our local region appeared to be lopsided, drawn toward something unseen, the culprit. A concentration of mass so immense it bends the very fabric of spacetime around it, tugging galaxies like a cosmic magnet. But here's the puzzle: the Great Attractor isn't just one object. It's part of something far grander, the Laniakea supercluster, a sprawling network of galaxies spanning over 500 million light-years. Think of Laniakea as a cosmic watershed, with galaxies flowing like rivers toward its gravitational center, the Norma cluster. The Great Attractor sits near this core, acting as a focal point for this vast celestial dance. For decades, peering at the Great Attractor was like trying to see through a foggy window. The Milky Way's own galactic plane blocks our view, absorbing visible light and radio waves. But infrared and X-ray telescopes have pierced through the dust, revealing clusters of galaxies and superclusters intertwining in ways we're only beginning to understand. One theory suggests the Great Attractor's pull might be amplified by even larger structures beyond it, like the Shapley supercluster, a behemoth of galaxies 650 million light-years away. What does this mean for us? The Great Attractor reshapes our understanding of cosmic flows. It's a reminder that gravity doesn't just bind planets to stars, it sculpts the universe on scales so vast they're almost incomprehensible. And while we've mapped its influence, the full story of what lies in that hidden sector of space remains one of astronomy's great ongoing detective stories. Every new observation peels back another layer, showing us just how much we still have to learn about the forces knitting the cosmos together. shifting gears from the vast gravitational pull of the Great Attractor, let's zoom into one of the most mind-bending discoveries in quantum physics, a structure that defies the very laws of time itself. Meet time crystals, a bizarre form of matter that never settles into equilibrium, oscillating indefinitely without any energy input. If that sounds like science fiction, you're not alone. Even Nobel laureate Frank Wilczek, who first proposed the idea in 2012, initially faced skepticism. How could something move perpetually without violating the laws of thermodynamics? Yet in 2017, two independent teams of scientists brought time crystals to life in the lab, opening a Pandora's box of quantum possibilities. So what exactly is a time crystal? Picture a diamond, but instead of its atoms repeating in space, its structure repeats in time. In ordinary matter, atoms arrange themselves in a stable, unchanging pattern when cooled to their ground state, the lowest energy configuration. But time crystals flip this idea on its head. Even in their ground state, their atoms oscillate in a predictable rhythm, like a clock ticking forever without being wound. This breaks what physicists call time translation symmetry, the rule that the laws of physics remain unchanged over time. Imagine a pendulum that swings back and forth on its own forever without friction or outside force. That's the eerie beauty of a time crystal. The secret lies in quantum entanglement. In a lab, scientists created time crystals using chains of ytterbium ions or diamond defects, coaxing them into this strange state with precisely tuned laser pulses. The result, a system that cycles between two configurations indefinitely, like a cosmic metronome. But here's the twist: unlike perpetual motion machines, which are impossible because they'd create energy from nothing, time crystals don't produce energy. They're a dance of quantum states, not an energy source, so the laws of physics remain intact, just stretched in fascinating new ways. Why does this matter? Time crystals could revolutionize quantum computing. Traditional qubits, the building blocks of quantum computers, are notoriously fragile, collapsing at the slightest disturbance. But time crystals are inherently stable, their oscillations resistant to external noise. Imagine a quantum processor that doesn't need constant error correction, where information is encoded in these unshakable rhythms. Researchers are already exploring how to harness this stability, potentially paving the way for error-free quantum systems that outperform today's supercomputers. Yet for all their promise, time crystals remain shrouded in mystery. Do they exist naturally in the universe, perhaps in the extreme conditions of neutron stars? Could they help us probe the fabric of spacetime itself? For now, these questions linger at the frontier of physics. But one thing's certain: time crystals remind us that the universe still holds wonders we've only begun to imagine, where even time, the most relentless force we know, can be rewritten by the quantum world's rules. Stepping away from the quantum strangeness of time crystals, let's turn our gaze to a cosmic anomaly so unsettling it's been dubbed the axis of evil. This isn't some apocalyptic prophecy, but a mysterious pattern in the oldest light in the universe, the cosmic microwave background, or CMB. Discovered in 2004 by NASA, a Wilkinson microwave anisotropy probe, this eerie alignment defies one of astronomy's bedrock principles, the Copernican idea that Earth holds no special place in the cosmos. The CMB is the afterglow of the Big Bang, a snapshot of the infant universe's temperature variations. These fluctuations should be randomly scattered like paint splattered on a canvas. But the axis of evil reveals something shocking. The hotter and cooler spots aren't entirely random. Instead, they show a puzzling alignment with the plane of our solar system, as if the universe itself is somehow aware of our little corner of space. To grasp why this rattles scientists, imagine throwing confetti in the air. The pieces should land in no particular pattern, but if they somehow arrange themselves into a shape matching your kitchen tiles, you'd suspect something was off. That's the level of unease the axis of evil stirs. It challenges the cosmological principle: which states that the universe should look roughly the same in all directions, with no preferred axis or center. Skeptics argue it could be a fluke or an artifact of measurement. After all, our view of the CMB is filtered through the Milky Way's dust and the motion of our solar system, which might introduce subtle biases. But even after accounting for these factors, the anomaly persists. Some theorists propose wild explanations, like the universe being shaped like a vast, rotating torus, or that we're seeing the imprint of a pre-Big Bang era. Others whisper about a cosmic defect, a crack in spacetime's fabric left over from the universe's birth. The axis of evil isn't just a curiosity, it could rewrite cosmology. If the universe does have a preferred direction, it might hint at deeper physics beyond our current models, like quantum gravity or multiverse theories. Or perhaps, as unsettling as it sounds, we're glimpsing evidence that our universe isn't as uniform as we thought. Either way, this cosmic riddle reminds us that even our most fundamental assumptions about reality might need a second look. So, is the axis of evil a statistical mirage or a crack in the foundation of modern cosmology? For now, it remains one of the universe's most tantalizing unsolved puzzles, a whisper that the cosmos might still be keeping secrets from us. Moving beyond the unsettling alignment of the axis of evil, let's dive into a cosmic mystery that could rewrite our understanding of the universe's hidden architecture: primordial black holes. Unlike the black holes we're familiar with, which form from collapsing stars, these enigmatic objects might have been forged in the chaos of the Big Bang itself. Picture the early universe as a roiling, dense soup of energy and matter. In such extreme conditions, tiny fluctuations in density could have collapsed under their own gravity, creating black holes the size of an atom or as massive as a star. These ancient relics, lurking unseen for billions of years, might hold the key to one of cosmology's biggest puzzles: the nature of dark matter. Scientists have long struggled to explain why galaxies rotate faster than they should, given the visible matter they contain. Dark matter, an invisible substance that interacts only through gravity, is the leading explanation, but despite decades of searching, no one has directly detected it. Enter primordial black holes. If they exist in vast numbers, they could account for the missing mass, weaving an invisible web that holds galaxies together. Imagine the universe as a tapestry, with these tiny black holes stitching together the fabric of space itself. What makes this idea so compelling is that it sidesteps the need for entirely new particles, like WIMP, weakly interacting massive particles, which experiments have failed to find. Instead, primordial black holes could be the dark matter we've been searching for all along. But how do we find them? Unlike stellar black holes, which reveal themselves by devouring nearby gas or bending light, primordial black holes would be nearly undetectable unless they pass in front of a distant star. In rare instances, their gravity could briefly magnify the star's light, a phenomenon called microlensing. Telescopes like the Subaru Hyper Subprime Cam are scanning the skies for these fleeting flashes, hunting for clues to their existence. Even more tantalizing is their potential link to gravitational waves, ripples in space-time caused by cataclysmic events. When two black holes collide, they send out these waves, which detectors like LIGO, Laser Interferometer Gravitational Wave Observatory, can pick up. Some of the collisions LIGO has observed involve black holes with masses that don't neatly fit predictions for how stars collapse. Could these oddballs be primordial black holes, remnants of the universe's fiery birth? If so, their mergers would offer a direct window into the early cosmos, revealing conditions we can't probe any other way. Of course, not everyone is convinced. Critics point out that if primordial black holes were abundant, we'd see more evidence of their effects, like distorted starlight or unexplained cosmic explosions. Yet, the universe is full of surprises, and the hunt for these ancient objects is far from over. Whether they're the missing pieces of the dark matter puzzle or just another cosmic curiosity, primordial black holes remind us that the universe's deepest secrets might be hiding in plain sight or in the darkest corners of space-time. So, are we on the verge of a breakthrough or chasing a phantom? One thing's certain: the search for primordial black holes is pushing the boundaries of what we know, and the answers could reshape our understanding of everything from galaxy formation to the very fabric of reality. Now, let's shift our gaze closer to home, to a discovery that reveals just how dynamic, and sometimes violent, our own galactic neighborhood can be. Rising like colossal chimneys from the heart of the Milky Way, the Fermi bubbles are two enormous lobes of superheated gas and gamma rays, each stretching 25,000 light-years above and below the galactic plane. Named after the Fermi Gamma Ray Space Telescope that uncovered them in 2010, these structures are a testament to the ferocious energy lurking at the center of our galaxy. What could have created such gigantic formations? The leading theory points to Sagittarius, a star, the supermassive black hole at the Milky Way's core. Astronomers suspect that millions of years ago, this cosmic behemoth experienced a dramatic outburst, a titanic release of energy as it devoured vast amounts of surrounding matter. Imagine a black hole feasting so violently that it burps out enough energy to sculpt bubbles spanning half the galaxy. The sheer scale is staggering. If these bubbles were visible to the naked eye, they would dominate the night sky, appearing larger than 30 full moons side by side. But the Fermi bubbles aren't just a spectacle. They're packed with clues about the Milky Way's past. The gamma rays they emit suggest particles are being accelerated to near-light speeds, likely by shock waves from the ancient explosion. Inside these bubbles, gas rages at temperatures of millions of degrees, far hotter than the surrounding galactic medium. This isn't just leftover debris, it's a cosmic crime scene, evidence of a cataclysm that reshaped our galaxy's core. Yet mysteries remain. Why don't we see similar structures in other galaxies? Is our supermassive black hole unusually active, or are we just catching it at a special moment in its billion-year life cycle? Some researchers propose alternative explanations, like a frenzy of star formation in the galactic center, or even dark matter annihilations. But the black hole outburst theory remains the most compelling, especially since similar, though smaller structures have been spotted in other galaxies with active cores. The Fermi bubbles also challenge our understanding of how galaxies evolve. Their existence implies that supermassive black holes don't just sit quietly, they occasionally erupt, injecting energy and matter into their surroundings in ways that can stifle star formation or even sculpt entire galactic ecosystems. This feedback process, as astronomers call it, might be crucial to explaining why some galaxies stop making new stars, or why certain regions of space remain eerily devoid of young, bright suns. What's next for studying these enigmatic bubbles? New telescopes like the upcoming Cherenkov Telescope Array aim to peer deeper into their gamma-ray glow, while X-ray observatories map their intricate structures in finer detail. Every observation brings us closer to understanding not just these bubbles, but the hidden life cycle of galaxies, including our own. The Fermi bubbles remind us that even our home galaxy has its secrets, and that the cosmos is anything but static. From the tiniest quantum fluctuations to these galaxy-spanning eruptions, the universe is alive with forces that shape reality in ways we're only beginning to grasp. Now, let's journey to one of the most puzzling voids in the cosmos, a place so vast and empty it defies ordinary explanation. Nestled in the constellation Eridanus lies a chilling anomaly, a colossal cold spot in the cosmic microwave background, the afterglow of the Big Bang. This isn't just a slight temperature dip, it's a gaping cosmic desert spanning an astonishing 1.8 billion light-years across. To put that in perspective, if our Milky Way were a grain of sand, the Eridanus supervoid would be the size of a football stadium. What makes this void so extraordinary? When scientists first mapped the cosmic microwave background, they expected tiny, random fluctuations, a cosmic fingerprint of the early universe. But the Eridanus supervoid stood out like a frozen thumbprint, a region significantly colder than its surroundings. At first, some dismissed it as a statistical fluke, but repeated observations confirmed its existence. This isn't just an absence of galaxies, it's a staggering deficiency of matter and energy, a place where the fabric of space-time itself seems unnaturally stretched. So, what could carve such a void? One leading theory suggests it's a remnant of an ancient collision with another universe. In the multiverse hypothesis, our universe might be one bubble among countless others, and the Eridanus supervoid could be a bruise left by a glancing blow from a neighboring cosmos. Imagine two soap bubbles bumping in a sink. Their edges would warp, leaving behind a dimple. If this theory holds, the cold spot might be our first tangible evidence of a reality beyond our own. But there are other, equally mind-bending possibilities. Some physicists propose that the void could be a cosmic texture, a defect in space-time left over from the universe's violent birth, like a wrinkle frozen in a crumpled sheet. Others speculate it's a sign of exotic dark energy, stronger in this region, pushing matter apart faster than elsewhere. Even quantum fluctuations in the early universe, magnified to cosmic scales, might explain this eerie emptiness. The implications are profound. If the supervoid challenges our understanding of dark energy or hints at a multiverse, it could rewrite the rules of cosmology. But not everyone is convinced. Skeptics argue that even a void this large shouldn't cool the cosmic microwave background as much as observed, suggesting our models of how light travels through such structures might be incomplete. What's next? Astronomers are scanning the supervoid with powerful telescopes like the Atacama Cosmology Telescope, searching for galaxies hiding in its depths or subtle distortions in the light that passes through it. Each observation sharpens the debate. Is this a window into exotic physics, a cosmic coincidence, or something even stranger? The Eridanus supervoid forces us to confront the limits of our knowledge. It's a reminder that even in the vastness of space, emptiness can be just as enigmatic as the stars. Whether it's a fingerprint of another universe or a flaw in space-time itself, this cosmic cold spot keeps us questioning, and that's where the best discoveries begin. But let's shift our gaze from the eerie emptiness of the Eridanus supervoid to a cosmic mystery that strikes at the very heart of physics, the enigma of black holes and the fate of information that falls into them. Imagine tossing a book into a fire. The pages burn, but the information, the words, the ideas isn't truly gone. It's transformed into smoke and ash, and in theory, you could reverse the process to reconstruct the book. But what happens if you throw that book into a black hole? According to Einstein's general relativity, the answer is terrifyingly simple. It's gone forever, crushed into a singularity where the laws of physics break down. This idea troubled Stephen Hawking so deeply that he sparked one of the most heated debates in modern physics. In the 1970s, Hawking showed that black holes aren't completely black. They emit radiation now called Hawking radiation, slowly evaporating over eons. But here's the catch: that radiation appears random, carrying no trace of the information swallowed by the black hole. If the black hole vanishes, the information vanishes with it, violating a sacred principle of quantum mechanics. Information can never be truly destroyed. This contradiction, the black hole information paradox, has divided physicists for decades. On one side, Hawking and others argued that information is irretrievably lost, a conclusion so unsettling it prompted bets, heated conferences, and even a famous admission from Hawking that he might have been wrong. On the other, quantum theorists insist information must escape, even if we don't yet understand how. Enter the firewall paradox. In 2012, physicists proposed a shocking solution: an inferno of high-energy particles at the black hole's event horizon, incinerating anything that crosses it. This firewall would preserve information by encoding it into the Hawking radiation, but at a ghastly cost. It would mean the smooth space near the horizon predicted by Einstein is an illusion, and an astronaut falling in would be vaporized long before reaching the singularity. But does this solve the problem or deepen it? Firewalls clash with relativity's core idea that free-falling observers experience nothing unusual at the horizon. Some theorists now argue the answer lies in quantum entanglement, where particles inside and outside the black hole are mysteriously linked, allowing information to leak out like a scrambled message. Others suggest black holes don't form singularities at all, but instead morph into fuzzy fuzzballs or holograms with their surfaces encoding everything that falls in. The stakes couldn't be higher. If information is lost, much of modern physics from quantum mechanics to thermodynamics needs rewriting. If it's preserved, we're on the brink of a theory unifying gravity and quantum mechanics, perhaps through strings, loops, or something even stranger. Today, physicists hunt for answers in the ripples of merging black holes detected by LIGO, in lab-grown analog black holes, and in ever deeper mathematical explorations. The paradox remains unsolved, but each twist in the saga reveals just how little we grasp about the universe's most extreme environments. One thing's certain: black holes aren't just cosmic vacuum cleaners. They're the ultimate laboratories testing our boldest ideas about reality itself. And the more we learn, the more we realize somewhere in their darkness the secrets of quantum gravity may be hiding. Now let's journey from the chaotic depths of black holes to a vast cosmic desert, a place so empty it defies our understanding of how the universe structures itself. Welcome to the Boötes Void, a staggering expanse of nothingness spanning 330 million light-years. To put that into perspective, if you dropped the Milky Way into this void, its nearest galactic neighbor would be tens of millions of light-years away. When astronomers first discovered the Boötes Void in the 1980s, they were stunned. In a universe where galaxies cling together in clusters and superclusters, this region is eerily vacant, containing only a handful of galaxies where there should be thousands. It's like walking into what you expect to be a crowded city, only to find a handful of houses scattered across an entire continent. So what could carve out such a colossal emptiness? One leading theory points to dark energy, the mysterious force accelerating the universe's expansion. If dark energy acted more intensely in this region long ago, it might have pushed matter away before galaxies could form, leaving behind this barren stretch. But there's a problem. Our current models of dark energy can't fully explain a void this size. Another possibility is that the Boötes Void is a remnant of an ancient cosmic collision. Picture two enormous soap bubbles merging in a bath. When they combine, the spot where they meet can form a thin, empty film. Some researchers suggest our void might be the aftermath of two massive, bubble universes brushing against each other in a multiverse, leaving this vast gap in their wake. And then there are the more speculative ideas. Could advanced civilizations have somehow harnessed the energy of entire galaxies, leaving this region barren? While the concept of alien megastructures like hypothetical Dyson spheres is fascinating, there's no direct evidence to support it. Still, the sheer scale of the void keeps even this possibility on the table as a tantalizing what if. What makes the Boötes Void particularly puzzling is how it challenges our standard model of galaxy formation. According to the widely accepted lambda-CDM model, matter should clump together in a web-like structure with voids, but none as extreme as this. Its existence forces us to consider whether our understanding of cosmic evolution is missing a crucial piece. Curiously, the void isn't completely empty. The few galaxies found inside it have unusual properties, with many showing signs of rapid star formation. Some astronomers think these galaxies might be late bloomers, evolving in isolation after being left behind by the universe's usual crowded environment. So is the Boötes Void a cosmic accident, a sign of new physics, or something even stranger? For now, it remains one of the universe's most bewildering puzzles, a gaping hole in our knowledge as vast as the void itself. But as telescopes grow more powerful, we may one day peer into this emptiness and find the answers hidden in its depths. Shifting our gaze from the eerie emptiness of the Boötes void, let's turn our attention to a fleeting cosmic whisper that sent shockwaves through the scientific community, the WOW signal. On a quiet August night in 1977, Ohio State University's Big Ear radio telescope picked up something extraordinary. A 72-second burst of radio waves so powerful and precise that astronomer Jerry Raymond circled it on the printout and scribbled, "Wow." Next to it in red ink. This wasn't just background noise. The signal matched the exact frequency scientists predicted an extraterrestrial transmission would use the hydrogen line at 1420 MHz, a universal hello channel chosen for its cosmic significance. What made the WOW signal so electrifying was its intensity. It was 30 times stronger than the ambient noise of deep space, and it appeared to originate from the direction of the Sagittarius constellation, near a star system called Chi Sagittarii. The signal's narrow bandwidth, just 10 kHz, ruled out most natural phenomena. Pulsars, quasars, and even passing satellites couldn't explain it. For a brief moment, it seemed humanity might have stumbled upon proof we weren't alone. Yet, the mystery only deepened when the signal vanished as abruptly as it appeared. Despite decades of follow-up observations, including targeted searches by the SETI Institute and even amateur astronomers, the WOW signal was never heard again. This absence fuels debate. Was it a one-time cosmic fluke, or did we miss our chance to reply? Some argue it could have been a reflected human transmission, like a rogue radio signal bouncing off space debris. But the Big Ear telescope was designed to filter out terrestrial interference, and no known human-made signal matched its profile. Another theory suggests a natural origin, like a comet's hydrogen cloud emitting a burst. In 2017, researchers proposed that two passing comets, neither discovered in 1977, might have been the culprits, but this idea crumbles under scrutiny. The comets weren't in the right part of the sky when the signal was detected, and their hydrogen emissions wouldn't explain the signal's precise frequency or strength. Then there's the tantalizing possibility of extraterrestrial intent. The signal's duration, 72 seconds, matches how long the Big Ear telescope could see a fixed point in space as Earth rotated. If aliens sent a beacon, they might have intentionally timed it for our tools, but without repetition, we can't confirm it. The WOW signal remains a cosmic riddle, a fleeting clue that challenges our grasp of the universe's possibilities. What's next? Modern telescopes like the Allen Telescope Array scan the skies with far greater sensitivity, but the WOW signal's ghost lingers as a reminder. Whether it was a cosmic coincidence or a deliberate call, it underscores how little we truly know and how much wonder still waits in the static between the stars. Now, leaving behind the tantalizing mystery of the WOW signal, let's steer our exploration toward another cosmic puzzle, one that sent scientists scrambling to rewrite the rules of gravity. The Pioneer anomaly is a story not of radio whispers, but of two intrepid spacecraft that refused to follow the expected path. Launched in the early 1970s, Pioneer 10 and Pioneer 11 were humanity's first emissaries to the outer solar system, tasked with studying Jupiter, Saturn, and the distant realms beyond. But as they ventured farther from the Sun, something odd happened. Both probes began slowing down slightly more than predicted by Newton's laws and Einstein's relativity. This tiny discrepancy, an extra deceleration of about 9 trillionths of a meter per second squared, might seem insignificant, but over decades and billions of miles, it added up to a glaring deviation. At first, scientists suspected mundane explanations. Perhaps fuel leaks or thruster misfires were nudging the probes off course, but meticulous calculations ruled these out. Then came wilder theories. Was an unknown planet tugging at them? Could dark matter be clustering near the solar system? or most tantalizing, was this a sign that our understanding of gravity itself was incomplete? Some physicists even proposed modifications to Einstein's theory, suggesting gravity might behave differently at extreme distances. The mystery deepened when other spacecraft, like Voyager and Galileo, didn't show the same anomaly. Why only the pioneers? The answer, when it finally came, was almost poetic in its simplicity. The culprit wasn't some exotic cosmic force, it was heat. As the probe's radioactive power sources decayed, they emitted infrared radiation, which bounced unevenly off the spacecraft's asymmetrical surfaces. This gentle push, like photons from a flashlight recoiling against your hand, was enough to create the observed deceleration. Yet, even with this explanation, the Pioneer anomaly remains a cautionary tale. It reminds us how easily unseen forces, whether thermal photons or quantum fluctuations, can mimic the fingerprints of new physics, and it underscores a humbling truth: our models of the universe are only as good as the data we collect. Today, missions like New Horizons carry lessons from the pioneers, their trajectories scrutinized for any hint of fresh anomalies, because in the quiet drift of a spacecraft, we might yet find clues to gravity's deepest secrets. What's next? As we push farther into the cosmos, each mission carries the potential to uncover forces we've yet to imagine, or to reveal, once again, how much we still have to learn. Just when we thought the Pioneer anomaly had taught us all its lessons, the solar system throws us another curveball, one lurking in the icy fringes beyond Pluto. Picture this: you're mapping the Kuiper Belt, that sprawling donut of frozen leftovers from the solar system's birth, and suddenly the objects vanish. Not gradually, but sharply, as if someone drew a line in the cosmic sand. Astronomers call this the Kuiper Cliff, and its existence defies everything we expect about how planetary systems evolve. The Kuiper Belt stretches from Neptune's orbit out to about 55 astronomical units, that's 55 times the Earth-Sun distance. Models predict it should be teeming with icy bodies for hundreds of farther, relics from the protoplanetary disk. Yet observations reveal a stark drop-off near the cliff's edge, with far fewer objects than anticipated. It's like walking through a forest that abruptly turns to barren land. What could cause such a dramatic boundary? One tantalizing theory points to an unseen, massive planet, dubbed Planet 9 by some researchers. This hypothetical world, estimated to be 5 to 10 times Earth's mass, could have shepherded Kuiper Belt objects into clustered orbits while clearing out a vast swath of space through gravitational kicks. Computer simulations show such a planet could explain not just the cliff, but also the peculiar orbits of extreme trans-Neptunian objects like Sedna, which loop far beyond the Kuiper Belt. The math fits, but where's the planet? Despite years of hunting, no telescope has spotted it yet. Then there's the disruptive past event scenario. Early in the solar system's history, a close encounter with a passing star, or even a rogue planet, could have stripped away the outer Kuiper Belt, scattering its objects into interstellar space. This would leave behind the cliff we see today, a fossilized edge of that ancient chaos. Supporting this idea are the odd orbits of some detached objects, which seem unmoored from the sun's gravitational grip, as if something violently disturbed them. But here's the twist: the Kuiper Cliff might not be a true edge at all. Some argue it's an observational bias, that fainter, more distant objects are simply harder to detect with current technology. New telescopes like the Vera Rubin Observatory could settle this by peering deeper into the belt's shadowy realms. Until then, the cliff remains a cosmic detective story, reminding us that even in our own backyard, the universe keeps its secrets well guarded. What's clear is that whether it's a hidden planet, an ancient upheaval, or a trick of the light, the Kuiper Cliff challenges our assumptions about the solar system's architecture. And as we'll see next, sometimes the most puzzling cosmic anomalies aren't in the void beyond Pluto, but in the strange visitors that pass through it. Now, just when we thought our solar system had shown us all its mysteries, the universe sent us a visitor from the stars, one that defied every expectation. In October 2017, astronomers spotted an object racing through our cosmic neighborhood, moving so fast it couldn't have originated here. Named Oumuamua, Hawaiian for scout or messenger, this interstellar traveler became an overnight sensation, not just for its origin but for its bizarre behavior. Unlike any asteroid or comet we've seen, Oumuamua was cigar-shaped, tumbling end over end, and lacked the telltale coma or tail of a typical icy body. But the real head-scratcher came when telescopes tracked its trajectory. It was speeding up slightly as it moved away from the sun, as if pushed by an unseen force. For comets, this isn't unusual. Outgassing when sunlight vaporizes ice, creating a jet of gas, can act like a natural thruster. But here's the catch: Oumuamua showed no visible signs of outgassing. No dust cloud, no icy particles, nothing. This left scientists scrambling for explanations. One camp argued it might still be a comet, just an exotic one. Perhaps Oumuamua's outgassing came from very specific patches on its surface, ejecting pure gas without dust, something we've never observed before. Or maybe its prolonged journey through interstellar space had baked its surface into a thick, carbon-rich crust, hiding any icy material beneath. If so, the gas could have seeped through cracks, nudging the object invisibly, but others proposed far wilder ideas. Could Oumuamua be a fragment of a shattered planet, a cosmic shard flung from another star system? Or most controversially, might it be artificial? The absence of outgassing and its peculiar shape led some, like Harvard astronomer Avi Loeb, to suggest it could resemble a light sail, a thin, reflective structure pushed by starlight, perhaps even a relic of alien technology. While most researchers consider this improbable, the very fact it's debated highlights how deeply Oumuamua puzzled the scientific community. The truth is, we may never know for sure. By the time we spotted Oumuamua, it was already speeding away, too distant for detailed study. Future telescopes, like the Vera Rubin Observatory, might catch more interstellar visitors, helping us unravel whether Oumuamua was a fluke or a sign of things to come. Either way, this cosmic oddball reminded us that the universe is far stranger and far more creative than our textbooks suggest. And as we'll see next, sometimes the most baffling cosmic puzzles aren't about visitors from afar, but about galaxies that defy the very rules of the universe itself. Now, shifting our gaze from mysterious interstellar travelers to something even more perplexing, a galaxy that seems to play by its own rules. In the vast cosmic dance of gravity, dark matter has always been the unseen choreographer, quietly holding galaxies together. But what happens when a galaxy defies this fundamental expectation? That's exactly what happened with NGC 1052 DF2, a galaxy that appeared to have almost no dark matter at all, a discovery that sent shockwaves through the world of astrophysics. First spotted in 2018, this ghostly galaxy, located about 65 million light-years away, was immediately unusual. Most galaxies, like our Milky Way, are teeming with dark matter, so much so that it outweighs visible matter by a factor of 5 to 1. Without it, galaxies would fly apart, their stars scattering into the void. Yet NGC 1052 DF2 seemed to flout this rule. Measurements of its stellar motions revealed something astonishing. The stars were moving exactly as predicted by the gravity of the visible matter alone. No extra mass was needed to explain their behavior. It was as if someone had removed the cosmic glue holding the galaxy together. The implications were staggering. If dark matter is truly the scaffolding of the universe, how could a galaxy exist without it? One possibility is that NGC 1052 DF2 is an outlier, a rare freak of nature. Some theories suggest it might have formed in a unique environment, perhaps near a massive galaxy that stripped away its dark matter through gravitational interactions. Alternatively, it could be the remnant of a violent collision where dark matter was torn away while the stars remained intact. But there's another, more provocative explanation. What if our understanding of dark matter, or even gravity itself, is incomplete? A handful of scientists have proposed alternative theories like modified Newtonian dynamics or MUND, which suggests that gravity behaves differently at cosmic scales, eliminating the need for dark matter entirely. While MUND has struggled to explain all observations, NGC 1052 DF2 reignited the debate, forcing astronomers to reconsider long-held assumptions. Yet the story took another twist. Follow-up studies revealed a second dark matter-deficient galaxy, NGC 1052 DF4, deepening the mystery. Were these cosmic anomalies or signs of a larger pattern? The discovery of more such galaxies could upend our models entirely. For now, NGC 1052 DF2 stands as a cosmic rebel, a reminder that the universe still holds surprises that challenge our deepest convictions. Whether it's a rare exception or a crack in the foundation of modern astrophysics, one thing is certain: the more we learn, the stranger the cosmos becomes. And as we'll soon see, sometimes the most puzzling forces aren't hidden in distant galaxies, but lurking right in the fabric of space itself. Now, turning from cosmic anomalies to a legend that has captivated imaginations for decades, the mysterious tale of the Black Knight satellite. This enigmatic object, often described as an ancient alien satellite orbiting Earth, has sparked countless theories, from extraterrestrial technology to forgotten human space missions. But what's the truth behind this enduring myth, and how does it reflect our fascination with the unknown? The story begins in the 1950s, when reports emerged of an unidentified object detected by ground-based radar. Newspapers and radio programs sensationalized the idea of a dark night watching over Earth, fueling speculation about its origins. By the 1960s, the legend had taken on a life of its own, with claims that this object was tens of thousands of years old, a relic of an advanced alien civilization or even a prehistoric human space program. Some even suggested it was sending signals, though no credible evidence has ever supported this. So what is the Black Knight really? The most plausible explanation is far less dramatic but no less intriguing. In 1998, during a spacewalk to install equipment on the International Space Station, astronauts spotted a strange, dark object drifting nearby. Photos of this debris, later identified as a lost thermal blanket, went viral, reigniting the Black Knight myth. Over the years, other sightings have been linked to known space junk, like discarded rocket parts or defunct satellites. Yet the allure of the unknown persists, blending reality with science fiction. The cultural impact of the Black Knight is undeniable. It's appeared in movies, music, and conspiracy theories, becoming a symbol of humanity's longing to uncover hidden truths. This legend taps into deeper questions. Are we alone in the universe? Could evidence of other civilizations be hiding in plain sight? While the satellite itself may be mundane, the stories it inspires reveal our boundless curiosity and the thrill of mystery. Yet there's a valuable lesson here. The Black Knight myth reminds us to question sensational claims while celebrating the wonder they evoke. Science thrives on skepticism and evidence, but imagination fuels discovery. Perhaps the real magic of the Black Knight isn't in its existence, but in how it challenges us to keep looking up, questioning, and dreaming. And as we'll see next, some cosmic mysteries aren't just about what's out there, but what lies beneath the surface of our own reality. But while legends like the Black Knight satellite spark our imaginations with tales of the unknown, science presents us with cosmic mysteries that are just as baffling yet grounded in hard evidence. One of the most perplexing of these is the cosmic microwave background cold spot, a strange anomaly in the afterglow of the Big Bang that has left researchers debating its origins for decades. This mysterious cold patch, discovered in 2003, spans nearly 1 billion light-years across the constellation Eridanus. It's significantly cooler than the surrounding cosmic microwave background radiation, the faint echo of the universe's birth and defies standard explanations. At first, scientists considered the possibility of instrumental error or gaps in data, but repeated observations confirmed its existence. So what could cause such a vast, unexplained chill in the fabric of space-time? One daring theory suggests this cold spot might be a bruise, a collision between our universe and another bubble universe in the multiverse. According to this idea, the energy of such an impact could have stretched space-time, leaving behind a region where the radiation appears colder than expected. It's a staggering concept, implying that our cosmos isn't alone but part of an infinite web of parallel realities. While this remains speculative, it aligns with certain models of eternal inflation, where new universes constantly bubble into existence. However, not all researchers are convinced. Skeptics argue that the cold spot could simply be a statistical fluke, an unlikely but natural variation in the cosmic microwave background. Others propose it's the imprint of a supervoid, an enormous region of space with far fewer galaxies than average. The lack of matter in such a void could subtly redshift light passing through it, creating the illusion of a colder spot. Yet even this explanation has holes, as no known supervoid matches the scale needed to produce the anomaly. The debate underscores a fascinating tension in cosmology. Are we seeing hints of physics beyond our current understanding, or just the quirks of probability? The cold spot challenges us to push the boundaries of science, probing whether our universe is truly alone or one thread in a vast cosmic tapestry. And as we continue mapping the heavens, anomalies like this remind us that some of the biggest discoveries might still be hidden in the faint whispers of the Big Bang's afterglow. Next, we'll explore another colossal structure that defies expectations, a wall of galaxies so immense, it stretches the limits of what we thought possible. As we venture deeper into the cosmos, we encounter structures so vast they defy our very understanding of scale and distance. One such marvel is the Hercules Corona Borealis Great Wall, a colossal filament of galaxies that stretches an almost incomprehensible 10 billion light-years across the universe. Discovered in 2013, this titanic formation isn't just a curiosity. It's a direct challenge to one of astronomy's foundational ideas, the cosmological principle. This principle states that, on large enough scales, the universe should appear roughly uniform no matter where you look. But the Great Wall shatters that assumption, presenting a region of space so densely packed with galaxies that it forces us to rethink the limits of cosmic structure. At its core, the Hercules Corona Borealis Great Wall is a chain of superclusters, each containing thousands of galaxies bound together by gravity. What makes it extraordinary isn't just its size, but its sheer improbability. According to our current models of the universe's evolution, structures this massive shouldn't exist. The Big Bang's afterglow, the cosmic microwave background, shows a remarkably even distribution of matter in the early universe. For something as concentrated as the Great Wall to form, the seeds of its structure would have needed to be planted impossibly early. Perhaps even before inflation, the universe's rapid initial expansion. Astronomers first detected this behemoth by mapping gamma-ray bursts, the most violent explosions in the cosmos. These bursts serve as cosmic signposts, marking the locations of massive star-forming galaxies. When researchers noticed an unusual concentration of them in the constellations Hercules and Corona Borealis, they realized they were looking at something unprecedented. The Great Wall's dimensions are staggering. It spans roughly a tenth of the observable universe, making it one of the largest known structures in existence. So why does this matter? The Great Wall doesn't just push the boundaries of size, it tests the limits of our physical theories. If the cosmological principle holds, the universe should look essentially the same everywhere at grand scales. Yet here we have a structure so massive that it skews the average distribution of matter in its corner of the cosmos. Some scientists argue it might be a statistical fluke, a chance alignment of smaller clusters that only appears as a single entity from our vantage point. Others suggest it could hint at exotic physics, perhaps evidence of primordial energy fluctuations far stronger than we've assumed, or even relics from a time before the Big Bang. What's certain is that the Hercules Corona Borealis Great Wall forces us to confront the unknown. Whether it's a flaw in our models or a glimpse into deeper cosmic truths, it reminds us that the universe is always more complex than we imagine. As we continue mapping the heavens, we may yet find more of these unimaginably vast structures, each one rewriting the rules we thought governed reality. Next, we turn to another cosmic test, a measurement that could reveal whether the universe's expansion is as straightforward as we believe. Shifting our gaze from the vast structures of the cosmos, we arrive at a subtle yet profound test that challenges our understanding of the universe's very fabric: the Tolman surface brightness test. Imagine looking at a distant galaxy, its light traveling billions of years to reach us. Conventional wisdom tells us that as the universe expands, this galaxy should appear dimmer and more spread out, its light diluted by the stretching of space. But what if the light itself is changing over time? This is the tantalizing question at the heart of the Tolman test, a measurement that could upend our assumptions about cosmic expansion. The test hinges on a simple but powerful idea: the surface brightness of a galaxy, how much light it emits per unit area, should behave differently depending on whether the universe is expanding or if light is simply losing energy as it travels. In an expanding universe, a galaxy's surface brightness diminishes with distance in a predictable way, following what's known as the inverse square law. But if light is aging or losing energy over cosmic distances due to some unknown process, the brightness would fade in a distinctly different pattern. By carefully comparing the apparent brightness of galaxies at varying distances, astronomers can tease apart which scenario matches reality. The implications are staggering. If the Tolman test suggests light is aging, it would mean the universe might not be expanding at all. Instead, the redshift of distant galaxies, the very phenomenon Edwin Hubble used to deduce cosmic expansion, could be the result of photons gradually losing energy as they journey across space. This would overturn nearly a century of cosmological consensus, forcing us to reconsider everything from the Big Bang to dark energy. Yet the test is fiendishly difficult to perform. Galaxies evolve over time, their stars aging and their structures changing, which complicates comparisons across cosmic epochs. Dust and gas between galaxies can also scatter or absorb light, muddying the measurements. Despite these challenges, modern telescopes like the Hubble and James Webb Space Telescope are refining the technique, using ultra-distant galaxies as cosmic time capsules. Early results tentatively support the expanding universe model, but the margins of error leave room for surprises. What makes the Tolman test so compelling is its ability to probe the universe's behavior without relying on assumptions about dark energy or the nature of gravity. It's a direct, observational check on one of cosmology's bedrock principles. Whether it ultimately confirms expansion or hints at radical new physics, this humble measurement reminds us that even the most established ideas must withstand the scrutiny of fresh evidence. As we continue to refine our tools and methods, the Tolman test stands as a quiet sentinel, watching for cracks in our cosmic edifice. Next, we'll explore a quantum phenomenon where mere observation can freeze time itself, a paradox that blurs the line between reality and perception. Now let's step into the bizarre realm where observation itself alters reality, a phenomenon so counterintuitive it seems ripped from science fiction. Imagine if staring at a pot could stop it from boiling, or watching a falling object could freeze it midair. This isn't magic, it's the quantum Zeno effect, a quirk of quantum mechanics where the act of measurement can literally halt the natural evolution of a system. Named after the ancient Greek philosopher Zeno and his paradoxes about motion, this effect reveals how deeply observation is woven into the fabric of reality at its smallest scales. Here's how it works. In the quantum world, particles don't follow the predictable paths we're used to in everyday life. Instead, they exist in a haze of probabilities, a superposition of states, until they're measured, forcing them to choose a definite property. But if you measure a quantum system repeatedly, fast enough, you can effectively trap it in its initial state. It's like flipping a coin but catching it mid-spin every nanosecond. The coin never lands, forever suspended between heads and tails. This isn't just theoretical. Experiments with atoms and photons have confirmed that frequent observations can suppress quantum transitions, almost as if time itself stalls under scrutiny. One of the most striking analogies comes from neutron stars, the ultra-dense remnants of supernova explosions. These cosmic powerhouses rotate hundreds of times per second, their surfaces bristling with magnetic fields so intense they can distort atoms. Some theories suggest that the extreme gravitational and electromagnetic environments near neutron stars might amplify quantum Zeno-like effects, potentially stabilizing unstable particles or even influencing radioactive decay. If true, it would mean the universe's most violent objects could harbor pockets of frozen time, where the rules of quantum physics are rewritten by sheer observational intensity. The implications stretch beyond astrophysics. Researchers are exploring whether the quantum Zeno effect could be harnessed for quantum computing, where maintaining a system's fragile state is crucial for processing information. By strategically observing qubits, the quantum equivalent of bits, scientists might prevent them from decaying into randomness, a major hurdle in building practical quantum machines. There's even speculative talk about using the effect to manipulate time perception, creating engineered systems where controlled observation slows down processes at a macroscopic scale. But the quantum Zeno effect also raises profound philosophical questions. If observation alters reality, what does that say about the nature of time and existence? Is the universe a dynamic tapestry only when we're not looking too closely? While we're far from answering these riddles, one thing is clear: the act of watching isn't passive. It's a force that shapes the cosmos, blurring the line between witness and participant. Next, we'll confront a mystery that tugs at the edges of our universe, an unexplained motion of galaxies that hints at something beyond the visible cosmos. Now, let's venture into one of the most unsettling cosmic mysteries, a silent river of galaxies drifting toward the unknown. While the universe expands in all directions, something peculiar is happening at the grandest scales. Galaxy clusters, those massive gatherings of hundreds or even thousands of galaxies, appear to be moving in unison toward a single point beyond the observable cosmos. This isn't just random motion, it's a coordinated flow, as if an invisible hand is gently pulling them toward the void. Astronomers call it the dark flow, and it challenges everything we thought we knew about the structure of the universe. The discovery of the dark flow came from painstaking observations of galaxy clusters using the cosmic microwave background, the afterglow of the Big Bang. Scientists noticed that these clusters were moving at astonishing speeds, thousands of kilometers per second, in the same direction, as if drawn by an immense gravitational force. But here's the problem. According to our current understanding, the universe's mass should be distributed evenly on large scales, meaning there shouldn't be any preferred direction for motion. Yet the dark flow suggests an imbalance, a gravitational tug from something so massive and so distant that it lies beyond the edge of what we can see. One explanation is as mind-bending as it is controversial. The dark flow might be evidence of other universes. In the multiverse theory, our cosmos is just one bubble in an infinite froth of universes, each with its own physical laws. If a neighboring universe happened to pass close to ours in higher dimensional space, its gravitational influence could be reaching across the void, pulling on our galaxy clusters like a magnet. Think of it as standing near an invisible waterfall. You can't see the water, but you feel its pull. If true, this would be the first tangible hint that we're not alone in the greater multiverse. But skeptics argue there could be more mundane explanations like errors in data or unknown local effects. After all, the dark flow's signal is faint, buried in the noise of cosmic measurements. Some suggest it might be an artifact of how we map the cosmic microwave background, or even a remnant of the universe's early asymmetry. Yet repeated studies have only deepened the mystery, with newer observations confirming that the flow extends farther than initially thought, billions of light years, far beyond where any known structure should exert influence. The implications are staggering. If the dark flow is real and not a measurement fluke, it means our universe is not as self-contained as we believe. There might be structures so colossal, perhaps other universes or remnants of a pre-Big Bang era, that their gravity leaks into ours, warping the motions of galaxies on an unimaginable scale. It's a humbling reminder that for all we've learned, the cosmos still holds secrets that defy our models and expectations. As we ponder this enigma, one thing becomes clear: the dark flow isn't just a curious anomaly. It's a potential window into realities beyond our own, a clue that the universe might be far stranger and more interconnected than we ever imagined. Next, we'll explore another quantum oddity that turns the vacuum of space into a cosmic funhouse mirror, where even emptiness isn't what it seems. Now, let's shift our gaze to a phenomenon that bends the very fabric of reality for those in motion, where even the emptiness of space becomes a stage for quantum theatrics. Imagine you're floating in what seems like a perfect vacuum, a void completely devoid of particles. To you, it feels like nothingness, but if you suddenly accelerate, say, in a rocket, something bizarre happens. The once empty space around you now appears to shimmer with particles, heat, and energy. This isn't an illusion. It's the Unruh effect, a startling prediction of quantum field theory that reveals how motion can literally change what we perceive as reality. The Unruh effect, named after physicist William Unruh, tells us that an accelerating observer doesn't experience the same vacuum as someone at rest. While a stationary person sees nothing, the accelerating observer detects a warm bath of particles, a type of radiation emerging from the void. These particles aren't just mathematical quirks. They're as real as the heat you feel from a fire, with a temperature directly tied to the acceleration. The faster you accelerate, the hotter this phantom glow becomes. Picture it like this. If you could stomp on the gas hard enough to accelerate at 1 trillion times Earth's gravity, the empty space around you would suddenly feel like a sauna at over 400 degrees Celsius. What makes this effect even more mind-bending is its deep connection to black holes. The Unruh effect is a close cousin of Hawking radiation, the process by which black holes slowly evaporate. Just as an accelerating observer sees particles in a vacuum, a black hole's immense gravity, a form of acceleration, creates radiation at its event horizon. Both phenomena arise from the same underlying principle. Quantum fields don't play by the same rules for everyone. A universe that's empty to one observer can be teeming with energy for another, depending on how they're moving. It's a cosmic reminder that reality is, at its core, deeply relative. But the Unruh effect isn't just a theoretical curiosity. It challenges our assumptions about the nature of emptiness and forces us to rethink foundational ideas in physics. For instance, in Einstein's theory of relativity, acceleration and gravity are two sides of the same coin. The Unruh effect suggests that this equivalence might extend into the quantum realm, blurring the line between motion and gravity even further. Some physicists speculate that understanding this effect could help bridge the gap between quantum mechanics and general relativity, the holy grail of modern physics. Yet detecting the Unruh effect directly has proven nearly impossible. The temperatures involved are incredibly faint unless the acceleration is enormous, far beyond what our current technology can achieve. But clever experiments using analog systems like sound waves in supercooled fluids have offered indirect glimpses, reinforcing the math behind the madness. These lab-based simulations suggest that the Unruh effect isn't just a mathematical artifact but a genuine feature of our universe. So what does this mean for our understanding of reality? The Unruh effect whispers a profound truth. The universe is far more dynamic than it appears. Empty space isn't just a static backdrop, it's a churning sea of potential where motion and perspective dictate what's real. Whether you see a void or a storm of particles depends entirely on how you're moving through the cosmos. It's a humbling lesson in relativity, one that ties the quantum world to the vastness of black holes and beyond. As we unravel these layers, another cosmic puzzle awaits, one that asks whether the entire universe might just be a fleeting thought in the mind of a randomly formed entity. But that's a mystery for the next chapter. Now, let's venture into one of the most unsettling thought experiments in cosmology, a puzzle that forces us to question whether our own existence might just be a fleeting statistical fluke. Picture the universe not as a grand stage for life, but as an endless sea of chaos where randomness reigns supreme. In this sea, given enough time and space, even the most improbable events could occur, including the spontaneous formation of a fully conscious brain, complete with fabricated memories floating alone in the void. This is the Boltzmann brain paradox, a mind-bending idea that challenges everything we think we know about reality, consciousness, and the arrow of time. The paradox is named after physicist Ludwig Boltzmann, who grappled with the nature of entropy, the measure of disorder in a system. Boltzmann's work suggested that over vast cosmic timescales, even in a universe tending toward disorder, random fluctuations could occasionally create pockets of order. In an infinite or near-infinite universe, these fluctuations might produce not just simple structures but complex, self-aware entities. Astonishingly, the math suggests it's far more likely for a single, isolated brain to pop into existence than an entire ordered universe like ours. So why do we find ourselves in a cosmos teeming with galaxies, stars, and life, rather than as lone Boltzmann brains drifting in darkness? This paradox forces us to confront the nature of perception. If consciousness can emerge from random quantum fluctuations, how can we trust that our memories, experiences, or even the laws of physics are real? After all, a Boltzmann brain would remember a past that never happened and observe a world that doesn't exist. Some physicists argue that the very fact we're having this discussion debating a universe that appears coherent and old is evidence against the Boltzmann brain scenario. If we were just random fluctuations, the odds of us perceiving a consistent, stable reality are vanishingly small. But the paradox doesn't stop there. It also ties into the concept of entropy and the fate of the universe. In a hypothetical heat-death scenario where the cosmos reaches maximum entropy and all energy is evenly distributed, Boltzmann-style fluctuations become the only events that could ever happen. Over incomprehensible timescales, even entire universes could blink in and out of existence. This raises a haunting question: is our universe just one such fluctuation, destined to dissolve back into chaos? Or is there something deeper, a law or principle, that prevents Boltzmann brains from being the norm? Critics of the idea point to the cosmic microwave background and the large-scale structure of the universe as evidence of a genuine, ordered past. Others propose that the paradox itself hints at flaws in our understanding of quantum mechanics or cosmology. Perhaps the universe isn't infinite, or maybe consciousness requires more than just random atomic arrangements. Some even suggest that the paradox is a reductio ad absurdum, a sign that our theories about the far future need re-evaluation. Yet the Boltzmann brain paradox endures because it exposes the fragile foundations of our knowledge. It reminds us that science isn't just about describing what we see, but questioning why we see it at all. As we peel back the layers of reality, we're left with a humbling thought. The universe might not owe us coherence, but until proven otherwise, we'll keep searching for answers, not as fleeting fluctuations, but as curious minds anchored in a cosmos that, at least for now, feels real. And with that, we arrive at the final frontier of our journey, where the line between reality and simulation blurs, and the very fabric of existence might be written in code. But that's a revelation for another moment, shifting our gaze from the chaos of Boltzmann brains to the precision of coded reality. We arrive at a theory that merges science with science fiction, the simulation hypothesis. Imagine for a moment that the universe as we know it, with all its galaxies, stars, and even our own consciousness, isn't a fundamental reality but an incredibly advanced simulation, like a hyper-realistic video game built by an unfathomably intelligent civilization. This isn't just a plot twist from a dystopian novel, it's a legitimate idea debated by physicists, philosophers, and tech visionaries alike. At the heart of the simulation hypothesis lies a simple but profound question. If a civilization could create simulations indistinguishable from reality, wouldn't it be statistically more likely that we're inside one of those simulations rather than the original universe? Think of it like this: if future humans or alien civilizations develop the computing power to simulate entire worlds with sentient beings, the number of simulated realities would vastly outnumber the one base reality. So the odds tilt heavily toward us being part of that digital majority. The evidence, while speculative, is eerily compelling. Start with quantum mechanics, where particles exist in fuzzy, probabilistic states until observed almost like a computer rendering details only when needed to save processing power. Then there's the mathematical precision of the universe. The laws of physics operate with equations so precise that some theorists, like Max Tegmark, argue reality might literally be math. If the cosmos runs on code, it would explain why math describes everything from star orbits to DNA. Even glitches in our perceived reality hint at something stranger. Have you ever experienced déjà vu, that uncanny feeling you've lived a moment before, or noticed cosmic coincidences like the moon and sun appearing the same size in the sky, enabling perfect eclipses? While these could just be quirks of nature, simulation theorists suggest they might be artifacts of a programmed environment, like subtle bugs in a vast computational system. Critics counter that the hypothesis is untestable, a modern-day brain-in-a-vat puzzle dressed up in tech jargon. They argue that invoking a simulator is like invoking a supernatural creator. It doesn't explain reality, it just pushes the mystery one level deeper. Plus, simulating every particle in a universe would require unimaginable energy, possibly more than the universe itself contains. But proponents fire back. A sophisticated simulation wouldn't need to render every detail at all times, just the parts being observed, much like a video game loads textures only when a player looks at them. The debate gets even wilder when you consider consciousness. If simulated beings can experience genuine self-awareness, does that make their reality any less real? And if we one day create our own hyper-realistic simulations, would that confirm we're likely in one ourselves? Elon Musk famously stated the odds we're not in a simulation are 1 in billions. Yet the simulation hypothesis isn't just a quirky thought experiment. It challenges us to rethink the nature of existence. If reality is code, then the programmers could tweak the rules, leading to alternative physics or even multiple versions of history. It also raises ethical questions. Would turning off a simulation be an act of genocide? And if we're in one, how do we wake up, or would we even want to? As we stand at this crossroads between science and philosophy, one thing is clear. Whether our universe is base reality or an elaborate construct, the act of questioning it, of pushing against the edges of what we think we know, is what makes us undeniably, beautifully human. And perhaps that's the most real thing of all. As we bring our journey through these 30 cosmic forces to a close, let's take a moment to marvel at just how strange and wondrous the universe truly is. From the quantum puzzles of particles blinking in and out of existence to the invisible grip of dark matter weaving galaxies together, each force we've explored peels back another layer of reality's grand illusion. Think about it, the very fabric of space and time might be a hologram. Black holes could erase information, and entire galaxies might be racing toward some unseen cosmic attractor. These aren't just wild theories, they're the frontiers of human understanding, challenging everything we thought we knew. What's even more thrilling is that this list barely scratches the surface. Every year, new discoveries force us to rewrite the textbooks. Maybe one day we'll crack the code of dark energy or finally detect a magnetic monopole. Or perhaps we'll stumble upon an anomaly so baffling it reshapes physics entirely. That's the beauty of science, it's never finished. So here's my challenge to you, don't just take these mysteries at face value. Question them, wrestle with them. Ask yourself what it means that the universe is held together by forces we can't even see. And while you're at it, let's keep the conversation going. Drop a comment below telling me which of these cosmic forces blew your mind the most. Was it the eerie silence of the Boötes void, or the way entangled particles communicate faster than light? I'd love to hear your thoughts. If you've enjoyed this deep dive into the universe's hidden gears, make sure to hit that subscribe button and ring the notification bell. There are plenty more cosmic mysteries waiting to be uncovered, from rogue planets to parallel dimensions, and you won't want to miss them. Until next time, keep looking up. Remember, the universe isn't just stranger than we imagine, it's stranger than we can imagine, and that's what makes exploring it so extraordinary.